So we have defined the Laplace transform, but if we keep computing Laplace transforms simply from the definition, we are not going that far. So we'll see that we can use some properties to make this the task of computing Laplace transforms easy. So let's see some Laplace transform properties. There are many. We are only seeing the ones that are more important now, and then probably I'll introduce others at the moment when we need them. So let's see what the fundamental properties are. So the first property is linearity. It's a sort of trivial property if we consider how it is defined, but if you want to compute the Laplace transform of the linear combination of two functions, so if you want to compute the Laplace transform of alpha 1 f1 of t plus alpha 2 f2 of t, so you have a certain function f1, you multiply that by a scalar alpha 1, and you also have another function in the time domain f2, and you multiply that by alpha 2, and then you add up alpha 1 f1 plus alpha 2 f2. If you want to compute the Laplace transform of this, you don't need to if you already know the Laplace transform of f1 and you already know the Laplace transform of f2. So this is given by alpha 1, the Laplace transform of f1 as a function of s, plus alpha 2, the Laplace transform of f2 t in s. So this is the first property, and it's very easy to prove, because if you are computing the integral from 0 to plus infinity of alpha 1 f1 of t plus alpha 2 f2 of t, so this is the one-line proof or two-line proof, in dt, if you are computing, the Laplace transform of this is the Laplace transform of the function that you obtain by scaling f1 and f2 and adding up the two scaled results. This is equal to, you apply the linearity of the integral, so this is given by alpha 1 integral from 0 to plus infinity f1 of t exponential of minus st in dt plus alpha 2 integral from 0 till plus infinity of f2 of t exponential of minus st in dt. So this is the first property that is quite trivial. We'll see that seems trivial, but it's also useful, and we'll see that we can do non-trivial things by applying it in a second. Let me just introduce other properties. Another property is the delay property. This property works like this. Sometimes you have a certain function f of t, and your function f of t, of course, has to be 0 for for negative t's, and then you have your function f of t, and this is your f of t. This function might be, you might want to compute the Laplace transform not of f of t, but of f of t minus tau. So let's see what happens if instead of having f, you have f of t minus tau. So if this is your time axis, it happens that your function here, you have it's 0 till time t equal to 0, and then it starts ondulating like this. In this case, it starts ondulating at time t equal to tau, and so it is 0 it's going to be 0. Well, I don't actually like what I've done here. It's going to be 0 until time t equal to tau, and then it will start having its behavior, whatever this behavior is going to be. So this is nothing but a delay by a time tau. So what happens if I already know my Laplace transform for the non-delayed version? Is there a relationship for the delayed one? So we simply compute it. We want to compute the integral from 0 till plus infinity of f of t minus tau exponential of minus st in dt. This tau is simply a delay, and we are assuming that tau is greater or equal than 0. If it's equal to 0, there is no delay, but the formula still holds. So, how do we operate? Well, we do a sort of trick. We keep our f of t minus tau here, and we write this as minus s of t minus tau here. But the problem now is that I have added a term tau here that I have to remove. So if I do this, if I consider this expression here, you can see that the two taus cancel each other out, and so we haven't modified anything. So the next step is now to apply a change of coordinates. So you see that the exponential of minus s tau is not depending on t, so it's a constant with respect to t, so it gets out. And now we have the integral from 0 till plus infinity of f of t minus tau exponential minus s t minus tau in dt. Now we apply a change of coordinates. Instead of having, we call sigma, for example. Sigma becomes our t minus tau. And so with this change of coordinates, this becomes exponential minus s tau. This becomes the integral. Now t goes from 0 till plus infinity. So our sigma needs to go from minus tau till plus infinity of f of sigma exponential of minus s sigma in d sigma. Now, since our function f of sigma is such that for negative sigma it's definitely equal to 0, then this can be written in this way: integral from 0 till plus infinity of f of sigma exponential of minus s sigma in d sigma. And so we can conclude that this is exponential of minus sigma tau times the Laplace transform of the original f. So what we can write is the Laplace transform of f of t minus tau for tau greater or equal than 0 is given by exponential of minus s tau f of s. In another way, if you have a delay in your function, the Laplace transform does not have a delay. It's simply multiplied by this exponential of minus s tau. Specifically, just let's convince ourselves that this is correct. When tau is equal to 0, nothing should change, and indeed when tau is equal to 0, this exponential minus s tau becomes 1, and so we are not changing. If there is no delay, the Laplace transform is actually not changing. Okay, so this is the delay property. And now we are going to see another important property, that is the following. The other property that we are going to see is the Laplace transform of a derivative. So let's assume that we know the Laplace transform of f of t, that is given by capital F of s, and we want to compute the Laplace transform of the derivative of f of t. So we want to compute the Laplace transform of the derivative of f of t, assuming that we know the Laplace transform of f of t. Let's see what happens by trying to compute it. We have the integral from 0 till plus infinity of the derivative with respect to time of f of t exponential of minus st in dt. Here we can apply integration by parts. If we apply integration by parts, so these are the two parts. This integral is given by f of t exponential of minus st computed from t equal to 0 and t equal to plus infinity minus the integral from 0 and plus infinity of f of t, and now I have to take the derivative of the exponential of minus st. The derivative with respect to time of the exponential minus st is given by minus s exponential minus st in dt. So this is what integration by part gives me. So let's proceed and let's compute this quantity here. Now we have to make t go to infinity if the real part of s is sufficiently large. So if we are in the domain of convergence, this quantity here goes to 0, because the exponential, if s is big enough, under some assumptions, mild assumptions on f of t, we can assume that this quantity goes to 0 when t goes to infinity. So we are left with minus this quantity f of t exponential of minus st that is being computed in 0. The exponential is equal to 1, so we are only left with f computed in 0 plus, now s, this s here is a constant with respect to t, so it comes out. So we are left with integral from 0 to infinity of f of t exponential of minus st in dt, and this is the Laplace transform of f of s. So we have that this is given by f of s multiplied by s minus f in 0. Here we are. So the Laplace transform of the derivative of f of t is obtained by a multiplication by s, and then we multiply the original Laplace transform by s, and we remove f of 0. Let's write this down. The Laplace transform of the derivative with respect to t of a function f of t is given by s times f of s. So let's write it in this way: Laplace transform of f of t as a function of s minus f 0. So we have seen that the Laplace transform converts derivatives into multiplications by the variable s, that is this frequency variable. And that's the main reason, this is one of the main properties, if not the main property, that makes the Laplace transform so important.